Hi everyone, I'm going to be reading Science Q&A, questions and answers for construction. Now this book is really long, so I'm not going to read all of it. It is available at the Mead Public Library if you are interested in reading more. But I'm going to pick out some of the questions and answers that I thought would be more interesting for you to hear. So this question is, how do skyscrapers withstand forces? And we're talking about forces being weather or storms and things like that. Skyscrapers are hundreds or even thousands of feet tall. Wind can be very powerful at these heights. Builders must plan for high winds when building these structures. Skyscrapers are built on steel skeletons made from vertical columns and horizontal beams for support. This skeleton is called the superstructure. Where the columns meet the base, the pressure is distributed evenly beneath the building. This is the building's substructure. The substructure often consists of layers of horizontal beams anchored in a thick concrete base. The substructure is often wider than the building itself, so it can fully support the weight of the building. With this system, the walls for each floor only have to support that floor's weight. How to best support a structure's weight is only one of many issues of concern for engineers. There are also outside wind forces such as earthquakes and wind. For example, if a gusty wind blows, a skyscraper can sway from side to side like a tree. While this movement may not damage the structure, it can make the occupants of the building uneasy. There is a way to lessen the effects of such forces. When a skyscraper is being constructed, crews tighten the points at which the vertical columns meet the horizontal beams in the frame. The building will then move as one solid object. As skyscrapers become even taller, this approach will not fix the problem. To keep taller buildings from swaying, engineers strengthen the building's core with steel supports and diagonal beams. This next question is, what do elevators do? In some form or another, elevators have been in use since as early as 300 BC. The very first elevators only traveled between a few floors. The first power elevator in the United States was a hoist that raised and dropped between two floors in a New York City building. Safety devices were installed to prevent the car from dropping if the hoist rope broke. This design change made it possible for elevators to carry people. The first passenger elevator was soon operating in a New York City store. Today, modern elevators carry thousands of pounds of freight and passengers up hundreds of floors, thousands of times each day. Without elevators, tall buildings would be useless. Even the most athletic visitor would shudder at the thought of walking up to the 99th floor. As buildings have become taller, elevators have become faster. The Tapali 101 Tower in Taiwan has elevators that race at a speed of 3,314 feet per minute. That is more than 3 times faster than the airliner climbs after takeoff. This next question is, how are bridges built? Anyone can build a basic bridge. If you have ever placed a plank of wood across a stream so you could cross without getting wet, you have built a bridge. However, bridges that support thousands of cars or people are much more complicated to build. As bridges span greater distances, the forces acting on them increase. Compression and tension are two forces that bridge engineers face. On a bridge, excess compression can cause the surface to buckle, and excess tension can cause it to snap. To avoid these problems, bridge designers spread the pressure out over a large area. For example, a beam bridge consists of a long, solid beam that is supported by columns on each end. Pressure, such as traffic traveling across the bridge, is supported by the columns. On this type of bridge, compression acts on the top side of the beam, causing it to shorten in width. This compression creates tension on the lower part of the beam, causing it to lengthen. To correct the forces of compression and tension, bridge designers increase the width of the beam. Most often, steel or concrete beams are added to bridge designs in order to support the weight of the structure. Designers often add a lattice to the beams. A lattice is a system of triangles placed together to make the bridge more rigid. It further absorbs the forces of compression and tension. Designs vary depending on the type of bridge, but the science of compression and tension is always in designers' mind. And this is kind of a cool fact. In the early 17th century, a bridge was built in Lima, Peru. Instead of using water to mix the cement, the builders used 10,000 egg whites. The bridge, known as the Bridge of Eggs, is still standing. That's pretty cool, huh? Another question are, how are dams built? Okay, a dam is a structure that blocks water from flowing out of a particular area. Dams are used to prevent flooding, provide water for farmland, and generate electricity. And there's quite a few very famous dams in the United States. Okay, this book does have a cool find it quick. Okay, so you can go to http pbskids.org/activity/sci/buildadam.html to try building your own dam. This is kind of cool, so if you need something extra to do over the summer, give it a try. The first step in building a dam is to remove water from the construction site. Cofferdams are erected around an area of water, and the water is pumped out to keep this construction site dry. Concrete tunnels divot the water around the construction site. Construction workers can then build the framing for the foundation and pour concrete. The pressure of water against the dam can destroy a poorly constructed or designed dam. The water exerts hydrostatic pressure that must be taken into consideration. Designers also consider uplift, the upward force caused by water pressure on the dam's foundation. Once these and other factors are incorporated into design, a dam can be built. Dams serve an important function, but there are serious drawbacks to them. Damming waterways can cause environmental problems. For example, animals may lose their water supply. Dams are also very expensive to build. Okay, so here it says dams can be controlled to release water at certain times. This raises or lowers the water level when necessary. Once a dam is completed, the cofferdams can be removed. Sometimes cofferdams are kept so they can be used for maintenance and repairs. Inflatable dams are a new way of controlling water. These dams have a thick rubber tube or concrete foundation and computerized controls. These dams can be inflated to about 9 feet high. The dams can be deflated to allow floodwaters to pass or to drain a body of water. Inflatable dams are useful because they deflate quickly and easily, preventing upstream flooding. That's pretty cool. I didn't know that. So this question is, how do buildings keep people safe? Researchers are developing ways to reduce the damage done to buildings by earthquakes. A material called and I'm going to have trouble pronouncing this, so just stick with me. Magnetorheological fluid, or MR fluid, is being used to keep buildings steadier during earthquakes. Now, this isn't really a problem in Wisconsin. We don't have a lot of earthquakes, but in California, in Nevada, where they have a lot more earthquakes, this is a big problem. So it's important that buildings keep people safe even during times of environmental concerns. So, MR fluid can turn into a solid in the presence of a magnetic force. Once the force is removed, the substance becomes liquid again. Wow, that's pretty cool. MR fluid is placed in containers called dampeners. Dampeners sit on the floor of a building. They are attached to braces and beams. During minor earthquakes, the MR fluid inside the dampener stiffens. This allows the building to sway with the vibrations, minimizing the shock. In the case of severe earthquakes, the MR fluid inside the dampeners becomes solid. This prevents major damage to the structure of the building. MR fluid helps the dampeners apply more force to stabilize the building. This technology saves lives and keeps buildings standing during earthquakes. Dampeners can be used to protect buildings, bridges, roads, oil rigs, and homes. There have been several major earthquakes in North America throughout history. In 1700, one of the most powerful earthquakes in history occurred over 600 miles along the west coast of North America, killing entire villages of American Indians. The earthquake caused severe damage as far away as Japan. Now, just because they have these dampeners does not mean that there will not be damage to the building. In fact, there will probably be lots of furniture broken and windows broken and things like that. But what they're saying is that the building won't come down. That the building itself will remain standing even if there is some damage on the inside due to the earthquake. And this keeps people safe. Because if you're in a 100-story building, you could just imagine during earthquake, if that comes tumbling down, that's not so good for you. So this will keep people alive in the buildings, even if there is some damage inside the building instead of outside. If that makes sense. All right, that's all I'm going to read of this story today. I did see this in the back of the book, and even though we are going to do a bridge with craft sticks, if you need something else fun to do and you have toothpicks, mini marshmallows, popsicle sticks, and glue at your house, you could try building a bridge with these materials. So just an extra fun thing to do with stuff that I know a lot of people probably have at their house. So it says what to do. Poke a toothpick halfway through the sides of 2 marshmallows. Then poke another toothpick halfway through the top of each marshmallow. Poke another toothpick, through the halfway through the top of each marshmallow. Poke the other ends of the toothpicks into another marshmallow. This forms a triangle with a marshmallow at each point. Continue connecting toothpicks and marshmallows until you have 3 triangles. This will make up one side of the bridge. Repeat this process to build the other side of the bridge. Place one side flat on the table. Then place toothpicks through each corner of the triangles. Connect the other side to the bridge to these toothpicks. This completes the frame of the bridge. To build the roadway, glue popsicle sticks to the bottom section of the bridge. Test the strength of the bridge with items from around your house. All right, so this is just another way to build a bridge. Kind of cool. Give it a try if you have the items at home. Have a great day, guys.